Hey y'all, how are you doing? Today we're going to talk about extrema on an interval. The definition of extrema is let f be defined on an interval I containing c. The value of y at c, also known as f of c, is the minimum of the function f on the interval I if f of c is less than or equal to f of x for all values of x in the interval I. F of c is the maximum of f on I if f of c is greater than or equal to f of x for all x in I. In order to verify that something is a global max or an absolute max, a global min or an absolute min, you must always check your endpoints. Now, this is important when you are thinking about the verbiage here. So the absolute minimum has the same meaning as the global minimum, and the absolute maximum has the same meaning as the global maximum. So that is what is going on in that definition. We move down to the next definition and they talk about a relative extrema. Now, the difference between a relative... So I don't know when this thing stopped recording, so I'm going to re-record a little bit here. If I say the same thing twice, I apologize. At the top, you see that you need to check your endpoints because the absolute maximum or the global maximum, both terms mean the same thing. And the absolute minimum and the global minimum, both terms mean the same thing. That means there is absolutely no higher point anywhere within that interval, or no lower point within that interval. But if you look down here at relative extrema, this little bump that the arrow is pointing to, that right there is a relative extrema on all reals. It is a relative max. It is not a maximum for everything because up there it says it goes all the way up to positive infinity. So it actually does not have an absolute maximum. Okay, we also have a relative minimum here on the interval I. That relative minimum is that lower bump. That lower bump is just a relative minimum because this function extends all the way down to negative infinity. Okay, I'm going to get rid of this mess here. It looks terribly messy. So we have a relative max and a relative min. However, if I were to close this off in such a way that I asked you what the maximum was on an interval and I closed it off in this way, that would change the max and the absolute max and the absolute min. Okay, it looks terribly messy when I do all of that with that. Okay, you're going to have a lot of questions on this in your heads, even if you can't say them out loud during class. I hope you say them out loud during class. If there's an open interval containing c on which f of c is a maximum, then c f of c is called a relative maximum of f. If there is an open interval containing c on which f of c is a maximum, then c f of c is called a relative maximum of f, or you can say that f has a relative maximum at c f of c. If there is an open interval containing c on which f of c is a minimum, then c f of c is called a relative minimum of f, or you can say that f has a relative minimum at c f of c. The relative maximum and relative minimum points are sometimes called local maximum and local minimum points. if we look at the graph in what is not called an example, but is, you see right there that you have the interval is defined from -2 to -15. Now, from -2 to, from -2 to +4. And we have an absolute max at that toppest point, that uppermost point, for 21. We can also see that the lowest point on this interval is -2, -15. It's a little cut off, but we can still read it. We also have a relative maximum, a relative but not an actual global, at 0, 5. And we have a relative minimum, not a global minimum, at 2, 1. I'm going to give you a minute to process that before I move on. Okay. A critical number or a critical point is, I put my words together wrong. A critical number or a critical point occurs when either the derivative equals 0 or it's not differentiable at f of c. That second piece is crucial. Quite often, students make the mistake of only remembering that critical values occur when the first derivative is 0. That is only part of the issue. You need to examine where the first derivative is 0 and where the first derivative is not differentiable at c. Critical values only occur where your first derivative is 0 or the function is not differentiable. Relative extrema only occur at critical numbers. Relative extrema can be absolute extrema if you can prove that there is absolutely no number higher or lower than them. Now let's look at our examples here. In example 1a, we have a minimum at 0, 1. We have a maximum or a global maximum at 2, 1, 2, 3, 4, 5. At 2, 5. But when we move along, we no longer have a maximum. We do have a relative maximum on an interval not stated. If I had said that we were examining from -1 to say 1/2, we would have a maximum at -1, 2. But that is not the interval specified by the graph. We have a minimum at 0, 1, and we have no maximum. Then we look over at C, we have no minimum, and we have a maximum at 2, 5. So if you look here, you see that in order for there to be a max and a min, what conditions are necessary to guarantee that there will be a maximum and a minimum? I keep thinking of words and I keep losing them. It really needs to be continuous, because if it's discontinuous, it might be discontinuous at the top or at the max or at the bottom or the min or on one of the endpoints, and one of the endpoints could be a max or a min. Okay, the extreme value theorem says that if f is continuous on a closed interval a, b, then f attains an absolute maximum value, f of c, or an absolute minimum value, f of d, for some numbers c and d in that interval a to b. This is even true if you have a horizontal line like that. Granted, your maximum and your minimum would be the same value, so that's not very useful. I can't imagine a world in which we would study that, but anything is possible. Okay, we're going to look at our guidelines for finding extrema on a closed interval. To find the extrema of a continuous function f on a closed interval a to b, use the following steps. First, find your first derivative and the critical numbers in that interval. Then evaluate each critical number in that interval, in the open interval. Then evaluate each endpoint. At the least of these values is a minimum, the greatest is the maximum. This is referred to as the candidate's test. So we take our first derivative, we find the value of our function when our first derivative is 0. Our value of x when our first derivative is 0. Once we've done that, we create our xy table. We find the value of our function at our endpoints and at our critical value. So when we go ahead and replace our values in both our endpoints and our critical value, we see that our minimum occurs at 4 and our maximum occurs at -1. So it does not say justify, so we can simply write that down, that our minimum occurs at 4, -49, and our maximum occurs at -126. Now we are going to find the minimum and the maximum, the absolute minimum and the absolute maximum, for f of x equal to 6x cubed minus 6x to the 4th plus 5. So our first job is to find the first derivative and set that first derivative equal to 0 and solve for x. And we solve and we see we have critical values at 0 and 3/4. Critical values, by the way, will not always be maxima or minima. Sometimes they're just something, a point at which some other interesting things happen in our graph. So keep that in mind. What I'm trying to say there is that if you do not find a max or min at a critical value, don't freak out and think you did something wrong. You may be completely correct. So now we're going to put these into our calculators and figure out what happens on the endpoints and on each of the critical values. And when we put them into our calculator, we see that our largest value occurs, or our maximum occurs, when x equals 3/4, and our minimum occurs when x equals 2. Okay, next up we have f of x equals 3x to the 2/3 minus 2x plus 1, and we're looking at that on the interval from -1 to 8. Again, we are trying to find the extrema on this closed interval, -1 to 8. And when you graph it, you see in that graph that you have something that looks like a minimum where x is 0, and you also have a maximum here, but it's not quite the total maximum, like the absolute maximum. I'm sorry, I can't believe I just used the word total. But you also see at -1 that you have a maximum there. But wait, there's more. You actually have an absolute minimum way down here. So we're going to explore with the table where those absolute maxima and minima occur, or where those local maxima and minima occur. In addition, I'm going to put up here the graph of the derivatives so you can see them for comparison. So here you see that at this cusp, you have an asymptote for the first derivative. And you see that at the local maximum, which is right here on the graph, your slope or your first derivative has a value of 0. So you're starting to see the correspondence of these graphs. In this third graph down here, I have put the two together so you can compare them. The skill of relating these two graphs is going to become critical and/or crucial to your understanding of calculus in about a hot second. So we are going to look at our values, at our critical values and our endpoints. So although we have a bump or a cusp at 0, 1, and we can call that a local minimum, it is not the global minimum. And this is asking for the absolute maximum and minimum, or the global maximum or minimum. And so the global maximum is actually occurring at an endpoint, as is the global minimum, or the absolute minimum. However, it is important to note that you do have some other extrema in this function, some other behaviors that determine the shape of your graph. Now we're going to move along to f of x equals sine squared x plus cosine x on the interval from 0 to 2 pi. So if we look at the graph, we can see that we have maxima occurring, I don't know where that is, maybe pi over 2 and maybe 3 pi over 2, I'm not really sure. And another one occurring down at pi, but we're going to check by putting our values into our calculator or working them out by hand. And I'm not going to bother graphing the first derivative here in the interest of time, because I'm almost up to 20 minutes here. Okay, a lot of this is pretty straightforward until we get to the cosine of x equals 1/2. And when we get the cosine of x equals 1/2, we need to make sure that we look at that and solve for x using our triangles. And we know, our 30, 60, 90 triangles and/or our unit circle. And we see that x equals pi over 3. And oops, I said 2 pi over 3, didn't I? I meant to say 5 pi over 3. So we go ahead and find those values, and we also need to examine our endpoints. Do we have our endpoints included in this? Yes, we do, 0 and 2 pi. So we go ahead and create our table. Okay, now we look at this and we see that we have a maximum. We have two maxima. They're the same, they give you the same y value. So we say that we have a maximum at pi over 3, 5/4, and 5 pi over 3, 5/4. And our minimum only occurs once on this interval. And our minimum, and this is an absolute minimum on this interval. Ooh, having trouble with my eye. Our minimum is at pi -1. Now, you should note that you do have some other bumps going on there, some other interesting things going on with that graph, and that is important information going forward. It's not important information today, but I'm trying to get you ready for what's coming. Okay, on to the mean value theorem. Okay, if a function f is continuous on a to b, the closed interval a to b, and differentiable on the open interval a to b, then there is at least one number c in the open interval a to b such that, okay, back up the truck for a second. This open interval right here means that it does not need to be differentiable on its endpoints. If all of this is true, then there has to be one number c in the open interval AB such that the derivative at c equals some parallel tangent line, or otherwise said, the slope at c equals some parallel slope of some secant line in that same interval. Give me a second. So again, you have some secant line going through the points A and B, which are the endpoints, and we're looking at the slope there. That must be the same slope as some tangent line. There exists some tangent line with exactly the same slope, and we're going to discover that the tangent line, the point at which that tangent line occurs. Equally important, if f of a and f of b, the y values at a and b are equal, this is a special case of the mean value theorem called Rolle's theorem. And Rolle's theorem states that, so again, Rolle's theorem is just the mean value theorem. It's a special case of the mean value theorem. And it's important that you understand this because there's nothing new to see here except for the name Rolle. So we hop down to example 1, and we need to show that the conditions of Rolle's theorem are met and find the C that Rolle's theorem guarantees. So it is important that you state that the polynomial is continuous everywhere. Therefore, f of x is continuous on the interval, the closed interval from -2 to 3. Polynomials are also differentiable. All polynomials are differential everywhere. So the function is also differentiable on the open interval -2 to 3. You must also state that the value of f of -2 and the value of f of 3, in this particular case, they both happen to be 0. Sometimes they will not be both 0, but they will be the same value in order for Rolle's theory to hold true. So now we're going to look and we're going to figure out what f prime of x is, and f prime of x is just 2x minus 1, and we need to figure out what value of c makes that derivative 0 and solve for c. So we go in and we solve for c, and we see that, that c is 1/2. When we set our derivative f prime of c, or when we replace c with its value in the first derivative, we see, oh gosh, sorry, I'm trying to write and talk at the same time, it never works out. 2 times 1/2 minus 1 is in fact 0, so f of prime of c is 0, and guess what else is 0? Bum bum bum, f of a minus f of b, and f of a was maybe f of 3. minus f of negative 2. You could have written that backwards, by the way. So we have found a tangent line that is parallel to the secant line of the endpoints. That final sentence is not crucial. You just need to find the c. You need to show the conditions of Rolle's theorem. You need to show that the conditions of Rolle's theorem are met and find the c. That is all you need to do. But I put that final statement in there so that you understand what just happened. We have found a tangent line parallel to the secant line connecting the endpoints when the slope of the secant line, I didn't have enough room to write that, is 0. Okay. Next up, given the function f of x equals 3 minus 5 over x on the interval 1 to 5, we are going to look at this visually and try to figure out what the mean value theorem is trying to find. So we draw in our secant line, and somewhere along the curve, we are going to have a parallel. Let's see if I can draw it. I cannot draw it, of course. A parallel tangent line. Oh, that's pretty close. And we need to figure out where that tangent line occurs. So now we need to show that the mean value theorem applies and find the c that the theorem guarantees. Once we have stated that it is continuous from 1 to 5 and it's differentiable on the open interval from 1 to 5, we can go ahead and say that the mean value theorem applies. Now, you can't just assert these things out of the blue. You actually have to know that they're true. So this right here, let me look at the function. It's only discontinuous when x equals 0. So it's both continuous and differentiable, and you can see that by looking at the curve. And there is no need to prove it beyond the point of stating it, but you also must be correct. So we can say that the mean value theorem applies. Once we say that the mean value theorem applies, we are going to set... Oh, I'm just going to stop there before I talk too much. So we find that first derivative, and we find the slope of our secant line, and now we are going to find the c that makes the c value where the slope of the secant line is going to be equal to the slope of the tangent line. So here, the slope of the secant line was 1. We found that down here. Once we found the slope of the secant line, we bring it up here, and we set it equal to f prime of c, and we are going to solve for c. We solve for c, and only one of these two values is actually in the interval, and we only need to state that value to be done with this problem. Right there is in fact our answer. You are driving a car on an interstate highway at 50 miles per hour and you pass a police car. 4 minutes later, you pass the second police car and you are again traveling at 50 miles per hour. The speed limit on the interstate is 60 miles per hour. The distance between the two police cars is 5 miles. That means that you traveled 5 miles in 4 minutes. Now, just using your intuition or common sense or tiny math abilities, not calculus math abilities, you know that you had to have gone more than 60 miles per hour. But now we're going to prove it using calculus. So first we need to show that we can actually use the mean value theorem. Distance is continuous and differentiable. We know that because you can't magically your distance can't magically not be measured, at least not in the reality that we know of. So now we're going to look and see what value of c would be occurring. And we see that at some point we had to have been going 75 miles per hour. Granted, this right here is not using like fancy schmancy calculus. This is more or less using common sense, using, what do we call it in chemistry? I don't know, unit conversion. You guys have some fancy name for it. I did not learn whatever that thing is called. So, in addition, if you allow yourself to think about it, you had to have been going somewhere between 60 and 75 miles per hour twice during that time. So you actually had to have gone over 65 miles per hour twice during those 4 minutes. You also had to have been going 70 miles per hour twice during those 4 minutes. Okay, if you're a real adult, you could continue arguing with the officer more and more, and the officer can actually give you infinitely many tickets because you had to have gone, what, I gotta look at the speed limit again. You 15 miles per hour, 60 miles per hour. So you had to have at some point gone 60.001 miles an hour, 60.1 miles an hour, 61 miles an hour, yada yada, you get the idea. So don't argue with the officer. In closing, I'm going to get slightly braggadocious. My uncle was just named the 5th most influential mathematician today. So I will put a link in today's blend page for you so you can see what he's been up to. He is responsible for proving most of Ramanujan's theorems. And Ramanujan is an Indian. If you want to know more about him, Vikas actually knows the name. But I'll put links. Bye.